Okay, hello everyone. Today, Dmitriy Panasenko is going to tell us about Deza graphs and vertex connectivity.
Okay, let's start at first, of course, the big thanks to the organizers and for chance to give me this talk. And I'm gonna start with probably very well-known definitions for the audience. I will start with the definition of strongly regular graphs and just remind you. So a k-regular graph on the vertices is called a strongly regular, or I will call it SRG for short, with parameters vk lambda mu if any pair of adjacent vertices has exactly lambda common neighbors and any pair of non-adjacent vertices has exactly mu common neighbors. And one of the most famous examples of strongly regular graphs is a Petersen graph. It has parameters 10, 3, 0, and 1. So any pair of adjacent vertices has 0 common neighbors, and any pair of adjacent vertices, for example, these two, have 1 common neighbors. It will be this vertex for this pair. And these graphs were introduced as a generalization of strongly regular graphs. Of course, you can generalize SRGs in many different ways, but these are graphs using this approach. So we keep the restriction that there are only 2 possible number of common neighbors, but we remove the fact that the vertices should be adjacent or not. So basically, for any pair of vertices, adjacent or not, the number of common neighbors can be either B or A, and we use parameters vk BA and say B is more or equal to A. And these are graphs with diameter 2 are called strictly Deza graphs. A small note here, so if parameter A is bigger than 0, then Deza graph automatically has diameter 2. But if A equals to 0, Deza graph can have diameter 2 or can have any diameter bigger than 2. For example, any cycle is a Deza graph with A equals 0. And here are 2 smallest examples of strictly Deza graphs. So this is Deza graphs that are not strongly regular and have diameter 2. For example, you can see that these 2 adjacent vertices, they have two neighbors, this one and this one. And these 2 non-adjacent vertices has also 2 common neighbors, this one and this one. It has parameters 8, 4, 2, 0, and the other example, it has parameters 8, 4, 2, 1. So the first graph is basically 2 clicks with matching, and the second graph is 2 4 cycles and 1 8 cycle connected in some beautiful way. And for parameter of these graphs, let us add 2 more parameters. We will call it alpha and beta. So alpha is the number of neighbors which has alpha, or not alpha, A common neighbors, and beta is the number of the neighbors which has B common neighbors. And it turns out that these parameters does not depend on the vertex we choose to define them, and can be actually calculated from the parameters K, B, and A, and V, of course, themselves. So I will not be talking about the formulas, but you can see it on the screen. And there are some restrictions for parameters of these graphs, not a lot of, but some at least. You can see it on the slide. So for example, B minus A should divide B multiplied by -1 minus K multiplied K minus 1. And if alpha does not equal to 0, then we have restriction for the number of vertices. V should be more or equal to K minus A. And if both of alpha and beta does not equal to 0, when we have this inequality as well. But basically, since these graphs are not so well structured as strongly regular graphs, we cannot have so many restrictions for the parameters. And Of course, there are some other restrictions, but the main one, basically just this 3. So now I will talk about enumeration. So in the first paper, when they were introduced in 1999, the complete list of strictly Deza graphs with at most 13 vertices was presented. When 12 years later, in 2011, an algorithm for enumeration of Deza graphs was presented by my ex-supervisor Sergei Gurayanov and my colleague Leonid Shalaginov, and this list was extended up to 16 vertices. And in 2019, this algorithm was reworked, and the list of strictly Deza graphs was extended up to 21 vertices. And small advertisement of the website I manage. You can go there, and the tables are available. The design is inspired by Brouwer's website for stronger regular graphs, heavily. Maybe if we have time, we can look on the website at the end of the talk. But otherwise, about the results, we were able to find 139 strictly Deza graphs with at most 21 vertices. And for 74 of these graphs, we were unable to find an existing construction. So it's just Deza graphs that appears from somewhere. We hope we can find a construction at some future. And this list can be extended because the enumeration was done not on a supercomputer, it was just regular desktop computer. So probably if we can have more powerful machine, we can go at least up to 23. 24 looks scary because it is divisible by 8, and it makes a lot of graphs, of course, when you have a lot of divisors. But let's work for some future. And the other subclass of Deza graphs I want to introduce and talk about enumeration as well is divisible design graphs. So a k-regular graph on the vertices is called divisible design graph, or DDG for short, with parameters vk, lambda 1, lambda 2, mn. If its vertex set can be partitioned into m classes of size n, and 2 distinct vertices from the same class has exactly lambda 1 common neighbors, 2 vertices from different classes has exactly lambda 2 common neighbors. So we have restriction for number of common neighbors as well, 2 possible values, lambda 1, lambda 2. So this definition implies that divisible design graphs are actually Deza graphs. And we will call DDGs with m equals 1 or n equals 1 or lambda 1 equals lambda 2 improper. And these DDGs actually are strong regular graphs with lambda equals mu. And otherwise, all other DDGs we will call proper. And further, we will consider only proper DDGs. One other comment about that. So for DDG, we can have diameter 2. Of course, if both lambda 1 and lambda 2 are bigger than 0. And we can have also diameter 3 if one of the values equals to 0, but we cannot have diameter bigger than 3. So we limit it in this case for divisible design graphs. So we will consider partition of vertex set of the graph gamma into the parts v1, v2, and so on vt. And with the property that every vertex of part v1 has exactly Rij neighbors in part vj. And then this partition v1, v2, etc. vt is called an equitable T partition of graph gamma. And the matrix with these coefficients, Rij, is called the quotient matrix of equitable partition. And if we talk about partition from the definition of the divisible design graph, it's actually an equitable, and we will call this partition a canonical partition. So here's an example. Once again, it is Deza graphs you're already seeing with parameters 8, 4, 2, 0. But now we will organize it according to definition, so we have to change 0 and 2. And the canonical partition is indicated by the color of vertices. So each color is the part of the partition. And we have this beautiful quotient matrix for canonical partition with all ones. And why these graphs called divisible design graphs? What does it have to do with designs? So let me also mention that. So an incidence structure with constant block size k is called a divisible design if the set of points can be partitioned into m classes of size n, such that 2 points from one class occur together in exactly lambda 1 blocks, and 2 points from different classes occur together in exactly lambda 2 blocks. Sounds very familiar, I assume. So basically very close to the definition of divisible design graph, and we will just multiply n by n to get v. And we call this divisible design symmetric if the dual of this design, or that is the design with transposed incidence matrix, is once again divisible design with the same parameters. And divisible design graph is graph whose adjacency matrix is the incidence matrix of symmetric divisible design. That's how DDG is connected to design theory and how they arise from designs. So at first, divisible design graphs were studied in master thesis by Muhlenberg, by supervision of Wilhelm Himmers, and the list of feasible parameters of divisible design graphs up to 50 vertices was presented. And in 2 following papers, feasible parameters of divisible design graphs up to 27 vertices were studied in more detail, and the existence of graphs was resolved in all but 1 cases. And all DDGs with lambda 1 equals k, lambda 1 equals k minus 1, lambda 2 equals 0, or lambda 2 equals 2k minus v were classified. So later I will be talking about some results on enumeration, and I do not show the results for these parameters because they are completely classified. And of course, one other nice property of DDGs is that they have at most 5 distinct eigenvalues. And I will not be reading them, but you can see them on the slides. And all eigenvalues can be calculated from parameters. And also multiplicities can, in some cases, can be directly calculated, but not in all cases. So, for example, we can have divisible design graphs with the same parameters, the same eigenvalues, but different multiplicities for these eigenvalues. It is possible. So in 2020, the extension of the algorithm for enumeration of Deza graphs was considered, and we were able to found at most, divisible Deza graphs with at most 39 vertices. Once again, if you're interested, please visit the website. But I will talk about the results right now in more detail. So this is the table. You can see not just all possible parameters. For example, as I made, you can look at the last 3 rows, and you can see the same parameters and different multiplicities and different number of graphs for different multiplicities. We have this line with dark blue. I will talk about it a bit later. We have 2 lines with dark red. This was the set of parameters we were unable to complete enumeration. We have this line in light blue. I will talk about that later as well. And the graphs for 36 vertices with red, they also were unable to finish the enumeration. Now I will talk about some construction that we were able to get from the enumeration results. So the first one is connected to distance regular graphs. So let us have an antipodal distance regular graph of diameter 3 with antipodal classes of size r, when we just denote by AI the matrix of relation to be at distance I for vertices. And if for this graph parameter lambda equals to mu plus 2, then we can give vertices with distance 1 and vertices with distance 3, make a new graph using this relation. And it actually turns out to be a divisible design graph with parameters you can see here on the screen. And there is an example of this construction. So half 6 cube is an antipodal distance regular graph with antipodal classes of size 2 and exactly lambda equals mu plus 2. And connecting antipodal vertices gives us divisible graphs with parameters 32, 16, 0, 8, 16, 2. And it actually has diameter 2, not 3. Now, the other construction, let us have a k-regular graph G with V vertices and the smallest eigenvalue lambda minimum. So a Hoffman-Kaklik for graph is a Kaklik meeting the Hoffman upper bound. I mean, the size of this Kaklik should be equal to V multiplied by lambda min divided by lambda min minus K. And the Hoffman coloring in graph is a partition of the vertices into Hoffman-Kakliks. So we can use it to construct divisible design graphs. Let us have strong irregular graphs gamma with parameters vk mu plus 2 mu. And such graphs should have a Hoffman coloring with Hoffman-Kakliks of size n. Also, let A be an adjacency matrix of graph gamma, in which Hoffman-Kakliks are located exactly on the main diagonal. So this blocks, basically. And let us define K as a matrix with this Kakliks on diagonal. I will be identity matrix. Then the matrix A plus K minus I exactly gives us an adjacency matrix of a divisible design graph. So we just basically replace the Kakliks with cliques, and we get divisible design graphs from strong irregular graph. I mean, Hoffman-Kakliks, of course. And also this set of parameters. And we can, for example, get 56 different divisible design graphs from 4 strong irregular graphs with this construction. We can get, because we can have different partition into Hoffman-Kakliks for these graphs. So we can get from triangular graph or Chang graphs with parameters 28, 12, 6, 4. We can have DDGs with parameters 28, 15, 6, 8, 7, and 4. The other constructions, so let us consider divisible design graphs with quotient matrix, which can be written as A with A's on main diagonal and B in any other entry. Let us take some copies of this graph, say S, and label all blocks of canonical partition in each copy with numbers from 1 to m. Then connect all vertices from blocks with the same label. We do not change adjacency inside the block. And we have divisible design graphs again if we have this beautiful equality lambda 2 equals to b equals to a plus s minus 2 multiplied by n. Another construction with quite same idea. So now we consider a symmetric divisible design. And every block contains the same number of points, k divided by m from each class. Then let gamma be the incidence graph of this divisible design. When we construct new graph, I denote it by gamma star, with the same vertex set as gamma. And in this graph, the vertices will be adjacent if they were adjacent before, or if these two vertices are points from different classes of divisible design D, or if these vertices are corresponding to blocks from different classes of dual design. If we have nice inequality 2 multiplied by m minus 1 multiplied by k divided by m equals lambda 2 plus m minus 2 multiplied by n, we can have divisible design graph as well. Another construction with similar ideas. So once again, we have the same divisible design as in previous one. But now we split the set of classes of blocks and the set of classes of point into pairs. We just get pairs and construct a new graph, gamma star, with the same vertices. And vertices are adjacent in gamma star if they're adjacent in original incidence graph, or if they are from different classes of the same pair of this partition. When if 2k is multiplied by m equals lambda 2, we can have divisible design graphs as well. Now the other construction with weighting matrix we were able to find. So a weighting matrix of order n and weight k is n by n 0, 1, minus 1 matrix, with property that if we multiply this matrix by transpose, we get identity matrix multiplied by some value k. So if we have 4t for t minus 1 weighting matrix W, and main diagonal of W contain blocks of zeros of size 4, then we can construct matrix A prime by replacing H0 with 0 matrix of size 2 by 2, each one with identity matrix of size 2 by 2, and each minus 1 with matrix of 1s minus identity matrix of size 2 by 2. Then this matrix plus this beautiful product gives us an adjacency matrix of divisible design graphs with parameters 8t, 4t plus 2, 6, 2t plus 2, 4, 2, 2. And we also can, this says construction 20, it should say construction 6, of course. If we have divisible design graphs from a previous construction, and the main diagonal of this matrix consists of this product, so basically this product. And this gives a partition of gamma into complete multipartite graphs with 4 parts of size 2, actually. Now we can construct new graph gamma prime by removing the h of the complete bipartite subgraph k for 4 from each part of this partition. And we once again can have divisible design graphs. Now, about some corrections for our enumeration. So this one is denoted by light blue in the table. In 2022, the tuple of parameters 32, 12, 3, 4, 7, 5, with spectrum 3 with multiplicity for 14, minus 3 with multiplicity 14, and minus 2 with multiplicity 6 was revised. And the number of non-isomorphic graphs with such parameters turns out to be 35, instead of more than 3,000 that we thought. That's has basically explanation that we were not enumerating this particular set of parameters because in Meilenberg master thesis, it was stated that there exists exactly 3,854 divisible design graphs with these parameters. So we decided to skip this enumeration, this particular parameters, but they revised it at 2022, and it turns out that only 35 graphs with these parameters exist. Why we have this big number? Because there are exactly 3,856 strong regular graphs with on 35 vertices. So basically this construction related to these graphs, and we thought that this number of first graphs gives exactly the number of divisible design graphs, which turns out is not the correct answer. And also in paper by Vladislav Vladimirovich Kabanov, a construction that allows to get all graphs with parameters 36, 24, 15, 16, 4, 9 was proposed. So we also know the number of graphs of these parameters, which gives us this table for unclassified or unenumerated graphs up to 39 vertices. So we have one graph on 27 vertices. We know sporadic construction, but we cannot generalize it. The other graph on 28 vertices, the same thing. We know sporadic construction, but we cannot generalize it. 16 graphs with on 28 vertices, we don't know the construction at all. We have two graphs on 32 vertices. We know the structure description, but we were unable to produce a construction. We know two graphs with at least two graphs with 32 vertices that are Kelly graphs. We don't know anything about this set of parameters. We suspect that divisible design graphs with these parameters does not exist, but we were unable to complete enumeration. We don't know anything about these two graphs on 35 vertices. For this set of parameters, we were able to find construction for two graphs. One remains unclassified. And this 30 graph on 38 vertices, we don't know the construction for them. So now we will be talking about vertex connectivity. And I think it's a nice place to have a question break if anybody wants to ask a question, because it will be kind of different topic. And if you have questions about enumeration results or the proposed construction, of course, you are welcome, I guess, to ask them right now. And when we go to vertex connectivity part of the talk, if it is okay, of course. Okay, seems like everything's fine, so we can move on and talk about vertex connectivity. So just to remind the definition, vertex connectivity of the graph gamma is a minimum number of vertices whose deletion from graph disconnects it in any way. And for example, there are some interesting results on vertex connectivity. Vertex connectivity of strong regular graphs is equal to the degree of the vertex k. It was proved in 1985. And a more generalized statement for distance regular graphs was proved in 2009. The same thing, the vertex connectivity equals to the degree of the vertex. When it's a natural question to ask, what about the other type of generalization of strong regular graphs? These are graphs. How big can be, or how small can the vertex connectivity be? Let's skip this slide. So this result for Deza graphs in general, let delta be Deza graphs obtained from strong irregular graph with eigenvalues R, which is a positive eigenvalue, and S, which is a negative eigenvalue, with construction called dual Seidel switching. I will be not going into details during this talk, but maybe a bit later if we have time. When we can have two following cases. The case for R equals 2 is not solved, so we don't know. But the case for R does not equal 2 was solved. The vertex connectivity of graph equals to the degree of the vertex, except for the case then gamma is a complement of n times n lattice. So by n times n lattice, I mean a graph that has like rows of this lattice are cliques, and the column of this lattice are also cliques. So basically this graphs we will call n times n lattice. And in this case, vertex connectivity is 1 less than the degree of the vertex. So now we have an example for these graphs that has a connectivity less than the degree of the vertex. But how far can we go? Let's start the more interesting part of the talk when we concentrate on divisible design graphs. So as I mentioned before, some divisible design graphs with some parameters were classified. And basically, let us start with results on these classified divisible design graphs. So if lambda2 equals 0, then vertex connectivity is once again the degree of the vertex. If lambda1 equals k, we have the same case. Vertex connectivity is the degree of the vertex. When, now things start to get more interesting. If lambda2 equals 2k minus v, when we can have two separate cases. If lambda1 does not equal k minus 1, then the vertex connectivity is k. But if lambda1 equals k minus 1, vertex connectivity is 1 less than k. And the other case, if for divisible design graphs with lambda1 equals k minus 1 and lambda2 does not equal to 0 or to k minus 3, because these cases were already considered, the vertex connectivity is once again 1 less than k. Still kind of same results as with Deza graphs. We already had examples with -1. So let's talk about Adamar matrices. Just a reminder, an M by M matrix H is called Adamar matrix if every entry is 1 or -1. And if you multiply this matrix by the transpose matrix, we get M multiplied by a AGT matrix. So if you remember, we were talking about weighting matrices. Weighting matrices are some kind of generalization of Adamar matrices. So we call Adamar matrix H graphical if it is symmetric with constant diagonal, and we will call it regular if all row and column sums are equal. Now we have this construction proposed in the first paper on divisible design graphs. Let us consider a regular graphical Adamar matrix H of order L squared, at least 4, with diagonal entries -1 and row sum L. Then the graph with adjacency matrix you see here, M and 0, this block matrix, and M and N can be calculated from our Adamar matrix with this block matrix form, J plus H, J plus H, J plus H, J plus H, divided by 1/2, and J plus H, J minus H, J minus H, J plus H divided by 1/2 for matrix N. And it turns out it is divisible design graphs with parameters you can see here. So let us consider this graph. And it's very easy to see that the vertex connectivity of this graph is at most 2L squared. But the value of k is actually 2L squared plus L. Why this happens? Very easy. We can remove this row of block matrix and this column of block matrix, and we have a disjoint union. So we have graph with matrix, adjacency matrix M, and graph with adjacency matrix N, just disjoint union of two graphs. So if we remove 2L squared vertices, which is exactly the number of vertices in each of these block matrices, we get a disjoint, disconnected graph. So very simple lemma. Well, it's at most 2L squared, but now we want to know the exact value. Let's go and return to the definition of some other properties of Adamar matrices before we continue. So if we have two Adamar matrices before, H1, not before, just H1 and H2, and then the Kronecker product of these matrices is Adamar matrix. Moreover, if they are regular with row sums L1 and L2, then the Kronecker product is regular with row sum L1 multiplied by L2, and the Kronecker product of two graphical Adamar matrices is graphical again. So basically, Kronecker product gives us nice construction for Adamar matrices. Now we basically consider these two Adamar matrices, H and H prime. And let me start by denoting matrix H by H1. When we can have this recursive construction, for any integer t, we denote by ht the canonical product of ht minus 1 and this matrix H prime. This matrix is regular graphical Adamant matrix of order 4 to the power t, with diagonal matrices minus 1 and row sum 2 to the power t. So basically, this matrix HT is exactly the matrix we need for construction that I described before. So if we apply this construction to this matrix, we have divisible design graphs with these scary parameters. And the smallest example is divisible design graph with parameters 24, 10, 6, 3, 3, 8. And this adjacency matrix. So D is just matrix of 1 minus identity matrix, and each block matrix has size 4. Each matrix in this block matrix. Now, we can apply recursive construction to this matrix to get our matrices with these parameters for bigger t's. So if we replace each d with this, each I with this, and each 0 just expanded with zeros, we get a recursive construction. And I will be calling this graphs gamma t to the top. Now we can go to these two subgraphs that were denoted by matrix M and matrix N in the definition of the construction. So the graphs that we left when we remove 2 to the power, oh, sorry, 2 to the power, 2 L squared vertices. Now we consider the subgraph at the top. We will call it gamma T1, and subgraph at the bottom with adjacent matrix N, we will call it gamma T top 2. Now about vertex connectivity of these graphs. So the graph gamma to the power T1 is divisible design graph with parameters you can see here, and its vertex connectivity equals to 4 to the power 2 plus 2 to 4 to the power t plus 2 to the power t. Basically, it equals the degree of the vertex. More interesting graph that actually turns out very interesting. So gamma T2 is divisible design graph with lambda 1 equals 0. Its vertex connectivity also equals to 4 to the power t, but that's not that interesting. More interesting fact that we have 0 here. And the diameter of this graph actually equals 2. So one graph is graph on 8 vertices. We already see this graph as an example of smallest strictly Deza graph. The other graph is divisible design graph with 32 vertices. We already met this example as well when we were talking about graphs from graph obtained from 6 halved cube. And before this result on vertex connectivity, it was only 2 known strictly Deza graph with A equals 0. So only 2 known graphs with A equals 0 and diameter 2. And accidentally, we were able to find a construction that gives infinitely many graphs of diameter 2 with A equals 0. So we still don't know probably there are other constructions for graphs with A equals 0 that have diameter 2, but we don't know exactly. And it is an open question just to know what are the strictly Deza graphs with A equals 2. A equals not 2, A equals 0. But let's return to the vertex connectivity. So now we considered the vertex connectivity of each part of after we remove 2 L squared vertices. We'll basically say that the vertex connectivity equals 2 multiplied by 4 to the power t. And if we return to the formula, you can see that the degree of the vertex is 2 to the power 2 multiplied by 4 to the power t plus 2t. So now we have proved that vertex connectivity can be the difference between vertex connectivity and the degree of the vertex can be any power of 2. So in some sense, these are graphs, and even divisible Deza graphs are not that nice as strongly regular, but I think that's quite interesting result. And actually, that's all for me. Thanks a lot for your attention.
Hey, thank you so much. Are there questions for Dmitriy? So I've been thinking, what can you say about the automorphism group of these graphs?
Which one are you talking about?
Do they have many symmetries?
No, everything can happen. So maybe, so they can have, even if we talk about these graphs in general, they can have V different eigenvalues.
Okay.
So even just every multiplicity is 1, so it's not that nice in that sense, if we talk in general. But if we go to divisible design graphs, they're way more structured, of course, and probably there are some results on automorphism group, but not so well known.
Are there asymmetric graphs that you know of?
Sorry?
Are there asymmetric ones?
In what sense? Probably yes.
The automorphism group is just the identity.
Yeah, probably, I think should be.